I turn up the level. Good. So there are two cases here, and the one I want to spend a little bit of time on is PG equals 2, k squared equals 1. And there's another case that you can do as a kind of little exercise, PG equals 3, k squared equals 4. Sorry, PG equals 3, k squared equals 2. So this one gives you x 2 to 1 to P2 with branch curve of degree 8. So you can just imagine that I've drawn a curve, a base curve of degree 8 in P2, and I'm taking square roots of some f8 in those coordinates. Or you can think of this as x8 in weighted projective space 1, 1, 1, 4. But in any case, this one is sort of well known, and everybody in classical Italian geometry knew how to do it without worrying about this artificial representation in weighted projective space. So that's just an exercise. So let's look at this one. So I told you the rules. The Riemann-Roch surfaces say that if I look at h naught of nkx, I get 1 if n is 0, and pg, which in this case is 2 if n is 1, that's just the definition, and then here I get 1 plus pg, this is chi plus k squared n choose 2 if n is greater than or equals 2. So I'm going to start building the ring R of x and kx. And what I find is in degree 1, I get two guys. So I'm going to call them x1, x2. Yes? Just to continue this calculation, degree 2, I get x1 squared, x1, x2, x2 squared, and y. Right, so the number I get here is 2, how do I do it? PG is, this is 3 plus 1. So I get 4. So here are quadratic in the xi's, and there aren't enough, so I've got to add another 1. So degree 3, degree 4, nothing very much happens. You just write down cubics and y times the quadrics, and then here you write down everything. This one includes y squared, and you just get the full complement. Nothing happens. So in degree 5, this is a sort of long calculation. You get quintics in x1, x2, so there are 6 monomials there. Right, the number we're trying to get to here is 6 plus 5 choose 2 is 10. I'm trying to get 16. I'm getting 6 from here. I'm getting S3 of the xi's times y. I'm getting x1, x2 times y squared. Yes. So I've got 6 here and 4 here and 2 here. I've got something slightly wrong here. 3 plus 10. Right, I'm trying to get 3 plus k squared. So I've got 6 here. I've got 4 here, which makes 10. I've got 2 here, which makes 12. And there's still one missing. Yes, so I put in Z. Yes, and then you can calculate 6, 7, 8, 9, and there are no more no relations, right? And then eventually we get this relation saying Z squared equals F10 of X1, X2, and Y. So this means homogeneous, weighted homogeneous of degree 10. The Y has weight 2. Yes, and so this tells us that X is X10 in P1125. Yes, so you don't have to think of this as having any geometric meaning at all. You can think of this as just I've put in the smallest possible number of generators of a ring with this numerical specification, and the smallest number of possible equations for it, and I get this. So if I choose generators x1, x2 of degree 1, y of degree 2, z of degree 5, and one equation in degree 10, I get a ring with exactly the right Hilbert, the right dimension in each degree. So I'll talk about Hilbert series and how all of this numerical calculation is not really needed in a minute, right? So let's think about how the Enriquez and his buddies would have thought about this. So let's look at the canonical system. Yes. So this is a pencil, a one-dimensional family of curves, and it's got k squared equals 1. So it looks like this. Right, so this is x1 equals 0, this is x2 equals 0, and they move around in a pencil here, and they've only got self-intersection 1. So that means the general curve has to be irreducible, and so the curve C in Kx is a curve of genus 2, right, because Kc is Kc plus C restricted to C is 2. Yes. And actually this is not just 2, it's twice the point P. Yes, so this point, the curve of genus 2 has a G12 on it. So in this case, Kc is a G12. And this point 2P is in G12. 2P is one of the divisors in the G12. So, I can, if I want to think of the curve, I want to draw it like this. This is supposed to be, this is the real, I'm drawing the real part, schematically the real part of a curve of genus 2. It's projecting down to P1. Right, and one of these points is singled out as a branch curve, and then there are 5 others. Yes, and so what I'm doing here is I'm taking, on P1 I'm taking 6 points, I'm taking the branch, the double cover of P1 branched in these 6 points, but one of the points is marked out for special treatment. Yes? So, this is all very simple, very easy, and restricting to the curve is always a first step in trying to understand what happens to the surface, right? So the next thing they would say is phi of 2k. Yes, and so this is a map from the surface X to this is a morphism of X to P3. Yes, and what can the image be? So 2k all squared is 4. And it's of course impossible, this is birational to that the map is birational, because a quartic would only have PG equals 1. You know, a quartic is a K3 surface, or if it's singular, it's a rational surface. Yes? And moreover, if I restrict this linear system 2K to any one of these curves, it's got to be the hyperelliptic double cover, right? And so this has to map to surface of degree 2 in P3. But it's not just a surface of degree 3, it's a singular surface, because every one of these curves passes through this point, right? And so the X has on it this family of curves like this, and they all pass through this point. And so what's happening here is that this is a quadric of rank 3. Right? And the canonical pencil on X comes from these curves moving around. Yes? So, you know, and then they say, well, this is a double cover, so we can study the branch locus. And again, you get sort of slightly curious considerations tell you that the branch curve has to be, there's a branch point there, so I'm supposed to be, X is supposed to be ramified at this point only. In other words, locally it's the double cover of this quotient singularity, and then it's got to be the intersection of the quadric with hypersurface of degree 5. Yes? And so I'm taking the square root of this picture as a double cover of the quadric of rank 3. So, you know, this is just much simpler to think of this quadric of rank 3 as being P112. So, you know, this is the conic with coordinates x1 squared, x1, x2, x2 squared, and then y is, I'm putting it in a projective space of dimension 1 bigger. Yes, and if you do that, then you don't have to worry about, you know, blowing up the singular point and understanding what happens there. This prescription gives you everything. Yes, and so, you know, this is a model for what you know, in the 1970s, I and several Japanese were looking at threefolds, what happens for threefolds, and this kind of phenomenon happens all the time, and you really can't get away. Here, you know, the Italian maestri could work at this and so on, and eventually, you know, by thinking very hard, they could understand what's going on here. But, you know, very soon, if you do threefolds, if you want to do three-dimensional analogues of this, then working with this kind of explicit geometry just doesn't work, just doesn't give you anything. Okay, so that's a little, that's kind of little historical digression. So I want to ask these questions. So what is P of, you know, A1, A2, A3? Let me say A0, AN. So I'm writing down these weighted projective spaces. So this one, you can think of it's just, I take the fourth Veronese embedding of P2, and then I take the cone over that. So, you know, if you really want to understand this geometrically, you can do it in classical terms, right? This one, I think you'll have sort of harder time explaining what it is, right? And, you know, the simplest way of presenting this is a weighted projective space. And, well, so it's proj of a ring. Let me say this, yes? And then can we understand what happens? So what would happen if, you know, X in P so if this is a hypersurface, for example, this might be f equals 0. In this case, this is a hypersurface to degree 10 given by this equation. But in other cases, so you know the good thing about this, if you think about this equation, I've got this equation z squared, and that means that it doesn't pass through this point. Yes, the hypersurface, you know, this thing, you know, I draw this as a kind of bag in the same way as the other things I did yesterday. When one of the x's is non-zero, the space is non-singular, and then, you know, there's the point py and the point pz, which are these quotient singularities, orbifolds, and the surface x is not passing through them. But what happens if x passes through the orbifold points? Right? In which case, you know, you have to understand. We're not just talking about understanding a hypersurface in the non-singular locus of the weight projected space, but we're thinking about this. And then 3, what is all this monomial counting? Right. So you know, here I'm just doing sort of what we used to do in classical theory of algebraic surfaces. I'm counting monomials. So I didn't tell you what happened in degree 3 and 4 or 6, 7, 8, 9, and you know, you can imagine doing it for yourself, or you can, you know, write it out formally as an exercise. But at the end of the day, I want a method of doing it systematically, getting rid of this. So systematic, and this is Hilbert series. So I'm going to talk about these problems today, and go on to some applications and some threefolds. So you know, just to sort of say, one of the things I'm going to talk about, I'm going to look at hypersurface of degree 7 in weighted projective space 1, 1, 1, 2, 3. Yeah, so this is a Q-Fano threefold. We're interested in its local behavior at the 1/2, 1, 1, 1, and 1/3, 1, 1, 1, 2 points. So these points, right? This is not a problem. This is something that's quite easy to explain, and I will do it. But I'm just trying to summarize some of the problems that I'm doing and why we want it. So the local behavior, and then I want to know that kx is O of -1. And then I want to know how I can, so eventually we want to understand also its birational geometry. So birational geometry means the geometry of birational maps from x to anything else or from x to itself. And that's something that now we know a very great deal about. We know it not just for this one, but for hundreds of other Q-Fano threefolds. Yes. So let me talk about the general proj. So I told you last time I've got R is direct sum Rn, and you know the rules as far as as far as this lecture is concerned, as far as this lecture series is concerned, you can do this, of course, more generally, but this is graded by positive integers. R0 is a field, and I'm just taking C for brevity, and each Rn is finite dimensional. And the Hilbert series is the thing that counts, is a generating function for this, for the dimension of these Rn. And R is finitely generated. So this just means that R is C of x0, x1 up to xn divided by some ideal. Yeah, so these are graded with weights xi, ai. So each of these generators ai belong to some one of the graded components of the ring, so they're forms of some given degree. Yes, and this is a homogeneous ideal. Homogeneous ideal just means that the ideal itself is also a direct sum like this of sub-vector spaces of each Rn, and they multiply in the obvious way, in the expected way. Yes? So the thing to notice is that graded is the same thing as a C star action. Yes. So if the ring is graded, then I just take lambda in there and I make lambda act on Rn. Acts by, so R lambda C star acts on the Rn acts by multiplication by lambda to the n. Yeah. So you know, there's the thing that's happening here. A representation of this group C star on a vector space automatically breaks up into eigenspaces. So C star is reductive. Its action on V splits V into eigenspaces, right, where it acts like this for lambda t. Yeah, so the character group of C star is hom C star to C star is just homomorphism of groups, and that's equal to Z. Yeah, so the n there is the character of the group, or maybe I mean Lie groups or topological groups or something. Yeah. So a C star having a grading on any vector space is exactly the same thing as having a C star action on a vector space. Yes, and so C star acts on R, and so it also acts on spec R. Yes, and so there's one other little thing I need to say. If I say direct sum Rn n greater than or equal to 0, sorry, n greater than, strictly greater than 0, this is MR, this is a maximal ideal. Right, so it's you know, it's the kernel. If I take the whole of this and project to C, the kernel is this maximum ideal. Yes, and so let's an ideal that contains MR to some power n. So ideal I contains that if and only if the variety of I inside spec R is 0. Yeah. And so, if I'm just talking about projective, the ordinary affine space, if this is a spec of just the polynomial ring, if the ideal there is nothing, then, here is the group action. So, the group action is doing this kind of thing. I mean, the orbits under this group action with this action are some kind of parabolas. It's best, they're monomial curves. They're certainly not straight lines. Yes, and so this point, the origin is a closed orbit of C star. Yes, and it's contained in the closure of every orbit. Yes, so if one of these orbits here is what happens when I take my point and I hit it by these powers of lambda. Yes, and if I let lambda go to 0, then I'm streaming into the origin. Yes, and so part of geometric invariant theory is that if I've got a group action and if one orbit is in the closure of another orbit, then you can always achieve that by passing through some copy of C star inside the group. So one parameter subgroups appear, in a kind of very fundamental way in geometric invariant theory or quotients by groups other than C star. So this is very general. This is very general stuff that you really need to know. Yes. In any case, the thing I'm going to do is I'm going to take spec. So I'm going to define proj R to be spec of R minus this irrelevant point. So this is called irrelevant. Right, and then divide this by the action of C multiplicative. Yes, and so this quotient is in the sense of geometric invariant theory. Yeah, so GIT is a complicated subject, and I don't think anybody really has ever really read and understood the whole of the book. But here it's really very simple, right? So what this means is, so this has an affine open sets of proj equal to, so I take f in Rn. So the f is n is greater than 0. So I take anything which is homogeneous. Yes, I take spec of I take the principal open set VF contained in spec of R. Yeah. So here's my R. right? If I'm talking about some open set that contains this point, then taking the quotient by the C star action is going to involve this problem that all of the orbits pass through one point. Yeah. So what I do is I say, right, I'm going to say f not equals 0, where f is some. So to get some principal open set here, Vf. Right, so this is the set of places where f is not equal to 0. Yes, and you know, this is something in algebra that's very easy to write down. This is spec of R of 1 over f. I take the ring R and I localize it by allowing in f as a numerator, as a denominator. Yes, and now the group action on this is very, very nice, right? All of the orbits are closed, and I can just take, so now what I want to do is inside here, I take R of 1 over f of degree 0. Yes, so this ring was homogeneous. The R was a graded ring. The f is homogeneous of some given degree, and so I take all of the polynomials here that are homogeneous of degree 0. Yes, and so this means this is a set of all g of degree nd divided by f to the power of d. Yes, in R of 1 over f. Yes, and so you know, I mean, when you write down rational functions, when you try to, you know, when you're doing the baby algebraic geometry in a first course, you write down, if you want to say what is a projective variety, you say it's a subset of projective space given by some equations, and then you have to say what the functions on it are. So you define a rational function to be anything like this, where the top and the bottom have the same degree. Yes? So having the bottom the same, top and the bottom homogeneous of the same degree means exactly that it's invariant under C star. Yes? And so this is, I take spec. So, Projar is covered by these spec of these rings of invariance, R of 1 over f 0. Yeah. I should have written square bracket. It doesn't really matter. I mean, I'm adjoining element to a ring. So this is a partial localization. Yes? And so, you know, you can do this for every f in Rn with n greater than 0. If f is of degree 0 and, you know, is non-zero, then you just get the empty set. So you get nothing at all. But, right. So it's enough to do only f equals xi. Yes, and this is what you do when you say that Pn is the union of A with xi not equal 0. Standard way of writing projective space as a union of affine places. This is what you're doing. Yes. Okay, so you know, this is the definition. This definition is, of course, exactly what is written in Untitled Chapter 2. I'm not doing anything here except explaining what it means. Yes, and so you know, this is a scheme. It has a structure sheaf. The open this is an affine piece of PROJAR, and the functions on it are, so the coordinate ring, the structure sheaf, is made from these these rings on the principal open sets. Yes. So now I want to explain why it is that this construction automatically leads to orbifolds. Right. So why do orbifold points occur? And so the point is this, that the group that's acting is C star, right? So this is acting on, you know, on this spec R. Right, so it's acting sort of like this. So it can, at some points in spec R are fixed by a subgroup of C star. Right? And this is necessarily some mu R inside C star. Yeah? So this is a group of roots V and C. So this is a group scheme if you want, but it's also just the finite cyclic group generated by exp 2 pi I over R. Yes? And so, you know, technically the thing that happens here is, so this is called isotropy. So when I'm taking the quotient by a group action, of course, set theoretically, I'm just taking a set of orbits. However, when the subgroup that fixes, when the isotropy group of an orbit changes, then you must get orbifold behavior. And this is only cyclic orbifold behavior. It's only this. So let me say, for example, if R contains the xi axis, sorry, spec R. Yes. So it might happen that all of the equations I write down vanish along the xi axis. So the xi axis is like this. Right. Then mu A fixes that orbit, and let's assume, for simplicity, that the other AJ a coprime to AI. Yes. Then you know, I get this picture which I mentioned yesterday. Right. Here is the C star action, and here is the xi orbit, the xi axis. Yes. So what I want, so the changing isotropy group, makes it impossible to take a slice of the action. Yes. So what a slice means, something that, you know, when you teach equivalence relations to undergraduates, you want to say we can choose a best representative of an equivalence class. So, for example, if I'm talking about numbers modulo 10, then, as we all know, the 7 is the equivalence class of -3 and 7 and 17 and 27 and so on. But we don't want to carry around with us this infinite collection of other representatives of the equivalence class. We just want to choose one. And so we say, right, I'm going to choose 0 up to 9. And then somebody might very well complain that -1 is actually a much easier thing to think about than 9. So choosing an equivalence class is choosing a slice. It's a kind of act of violence that you're doing to an equivalence relation, right? And so when I'm doing ordinary definition of Pn, I'm taking Cn plus 1, you know, coordinates, usual coordinates x0 up to xn, and then I'm going to say if xi, let's say if xn is not equal 0, then xi divided by xn, I equals 0 up to n minus 1, represents the equivalence class. Yes, and then we draw a picture. You know, here is the C star action spreading out in all directions, and I take xn equals 1, and every equivalence class hits that in exactly 1 point. Well, everyone except xn equals 0. Yeah? And so this is a slice of the equivalence relation, right? But here, if I choose xi to be 1, it hits the xi axis in exactly 1 point, but it hits every neighboring fiber in a mu ai orbit, right? So this is an attempt to slice, an attempt to choose a slice of the equivalence relation, and it hits neighboring orbits in a mu ai orbit. Yes, and you can't get away from this. You can't. So the solution to this is so we get cyclic phenomenon so you know, in terms of what I was writing down over there, I have to write down all possible monomials x to the m divided by xi to the power of ai, where this thing here is a monomial of degree divisible by ai. Yes, and this is the same calculation as invariance of mu ai action. Yes, and so my preferred way of thinking about this is let's take apart this mu I invariant. So, you know, we're trying to divide out by an algebraic group C star. Yeah, so if I can do something that sort of reduces that to a finite cyclic group, then I figure I've simplified the problem, right? So to do this, we introduce xi, right, which is the such that xi to the power of ai is xi. Yes? And now this one has degree 1. It has weight 1. So it's not actually in the ring. What we're doing is we're passing to a ring where the calculating these invariants is going to be easier. Right? So later on we have to pay a price for that, but I'm making a slightly bigger ring in which now I can just write down each of the xj's, each of the other xj's, and now xj divided by this same psi to the power of aj is now homogeneous of degree 0. Yes? And so now, together with this psi I, I'm just talking about a n. Yes? So this is a n with these coordinates. Yes? And now the quotient itself, the ring of invariance itself, is now a quotient by mu ai. Right, and it's acting on this thing here with acting by 1 over ai aj. Right, so it acts here. So what I'm doing here is I've got this bigger ring in which everything is very simple. Everything is just reduced to a polynomial ring or a quotient of a polynomial ring. Yes, and on the other hand, I have to get rid of this third quantity, of this root. So psi I is the ai's root of psi I, and I have to get rid of all occurrences of this root. And I do this by only allowing monomials here of degree divisible by ai. And that's the same as taking the quotient by mu, taking the ring of invariance of mu I, acting on this polynomial ring. Yes? And so this notation here, this notation means Cn with the action of the group mu ai. So this is just a cyclic group order ai. Acting with these eigenvalues, characters. Yes? So in this notation, this thing here is the thing we're dividing by, so it's sort of reasonable to put it in the denominator, and these are the characters of the group action. So these are integers modulo ai. And so, you know, it was a little bit of a simplification to say I can assume everything else is co-prime, and you know, it's not, it doesn't always happen exactly like that, but this is the basic idea. So when I take proj of a ring, if the ring is not generated in degree 1, then you must expect to see these orbifold singularities. Okay. So the second, so let me look at this X7 in weighted projective space, 1, 1, 1, 2, 3. Right. So you know, I've been doing this since around 1977 or something like that. Yes. And so I can do these in my head. The very first thing we want to know is what is the dimension of this space? right? And to do that, we do 1, 2, 3, 4, 5, minus 1 is 4. Yes? Next, what is the canonical class of this space? It is minus 1, minus 1, minus 1, minus 2, minus 3. So K of this projective space is minus 8. Yes? So if I want to write, if you think of the canonical class as being something to do with differential forms, which lots of people want to, then this is, I'm writing down dx1, wedge dx2, wedge dx3, wedge dy, wedge dz. Yes, and then I want to write down here some f to make everything homogeneous of degree d, of degree 0. Yes, and that means that this f has to be of degree minus 8. Right, and that's what this minus 8 is. Yes, so you don't really have to think of this as having any kind of theoretical content. I'm just telling you things you need to get used to when you're doing this calculation. Right? So this x is a Fano of index 1, a Q Fano of index 1. Yes? So he has kx is minus 8 plus 7 is O of minus 1. So again, you can think of this as, if this is given by, g equals 0, you can think of this as dx1 wedge dxn dz divided by g, and then I have to multiply this by something to make it homogeneous of degree. So, I mean, it's a bit more complicated than this, but this is a group, this is a quotient by C star acting like that. So I have to sort of work, I have to take out the Euler vector field corresponding to that, and then I have to take Poincaré residue from whatever form I have here down to x. So it's a bit more complicated than this, but you'd have to do it all in local affine pieces, and eventually you get this. So when you're doing the theory, it's sort of probably better to be in a different world and do it using the methods of commutative algebra. So I'll explain a bit about that tomorrow. Yes. So then, is this variety non-singular, or does he have orbifold singularities? So, you say, right, I've got this formula, this thing here, y. Can I have y to the n in the equation of x? And unfortunately, 2 does not divide 7. So this is impossible, right? And so the next best thing is I might have y squared z in the equation of x. Yes? Or failing that, y squared, y cubed times x. Yes? And having one of those is the condition. So let's write affine cone over x to be spec of this ring, polynomial ring of all these x's and y's and z's, divided by G7. Yes? So having one of those two monomials in the equation of G is exactly the condition for this C of x to be non-singular along the y-axis. So in other words, along the y-axis, I can assume that y is equal to 1, and that means I take this equation g, I take its differential with respect to z, and I set y equals 1. Right? So if this monomial is present in the equation of z, x, I get a non-zero Jacobian ideal, and that means that by the inverse function theorem, by the implicit function theorem, the cone of x is non-singular along y, along the y-axis. Yes? And so this means that at py, if this monomial is present, which is the preferred case, is the general case and the preferred case, so if y squared z is present, then at the point py, so this is the point 0, 0, 0, 1, 0 in x, x is 1/2 of 1, 1, 1. Right. So this the thing appearing here is the y, or the square of the, this procedure. I have to take the square root of y, and these things here are x1, x2, x3. So x1 over square root of y, x2 over square root of y, x3 over square root of y. These things are coordinates on the orbifold double cover of x. Yes. So this x, locally at this point, is the quotient 1/2 of 1, 1, 1. And the ones here are x1, x2, x3, and the half there is because I can only take invariants of order 2 of them. Yes, and similarly at pz, x is 1/3 of 1, 1, 2. Right. So z also doesn't divide 7. So, but I can write, for example, z squared times x1. Right, in that case, these are x2, x3, and y. Okay, so let me leave it at that for the moment. Okay. So these are just techniques of calculations, and you can easily, well, you can learn them if you spend a few weeks practicing.